We are discussing the different strategies to be followed for designing embedded systems. In the last class, we had looked at the hardware software partitioning problem, and we have seen how the tasks can be mapped to different processing elements depending on the cost constraints. Mapping of the tasks also imply scheduling of the tasks. Trying to do partitioning and scheduling, that is allocation and scheduling together, is a complex problem. But scheduling in a way is related to allocation as well. Here we shall look at a simple example to understand this problem. Let us consider this simple task graph. In fact, we have looked at similar task graphs in the past as well. Now, here this D1 and D2 indicate the communication cost between the tasks, and let us consider that we have got a hardware platform, that is M1 and M2 consisting of two processors. The problem is that of mapping the tasks onto these hardware elements. Okay? And the question is, if we are mapping them optimally, that means if we are doing the allocation of the tasks to processor optimally, then that would also determine their schedule and hence provide the result in minimum time. Let us consider that this is the cost or this is the execution time parameter that we already have for the purpose of mapping. So, I have got P1 which takes on both the processors time 5 units, P2 takes 5 on M1 and 6 on M2, and P3 can only be executed on M2 because of its special nature, and it takes time 5 units. Now, what will be the optimal allocation such that the complete task graph can be completed in minimum time? That means it implies scheduling as well. Assume communication within PE is free, that means there is no delay involved there, and cost of communication from P1 to P3 is 2 and cost of communication from P2 to P3 is 4. Okay. So, with this cost, if you look into it, so we can have one design where P2 gets mapped to M1 and P1 and P3 gets mapped to D2. So, in that case you are paying for this communication cost because I need to have the result from P2 coming to P3 for the final computation. So, the total time taken would be summation of this path, whether it turns out to be 15. Now, if we look at another design, here my allocation is that I allocate P1 to M1 and P2 and P3 to M2. That means, effectively I have interchanged P1 and P2 in terms of its allocation scheme. Here you will find that the cost is much less for communication because it is between the P1 and P3, and so the total time required turns out to be 12, which is less compared to the previous one. So, the whole point is that if we are trying to do the design in terms of optimizing time as well as maybe satisfying timing constraints, we need to look at allocation as well as a scheduling problem in a integrated fashion. In fact, partitioning, allocation and scheduling should be considered in an integrated fashion, and that provides us the basic framework or overall picture of hardware software co-design and hardware software partitioning. Now, picking up cue from there, we shall look into a new methodology of design which we call platform based design. Now, here the basic motivation is to reuse elements or components that has been designed to reduce design costs. It's similar in philosophy with that of your object oriented design and component based design, where we say that if you already have software components, we shall plug them in to develop an application. Here we are talking about components which are just not software components, but we are talking about both hardware as well as software components. So, what we say, the basic architecture of the implementation can remain fixed within a certain degree of parameterization. So, we have programmable cores, I/O, memory. A family of architectures that allow substantial reuse of software is what we call a hardware platform. In fact, this definition we had already considered when we discussed SOCs. Now, again we are going back to the platforms to understand the philosophy of embedded system design around platforms. Now, in fact, one point you should understand very clearly, that when we are talking about a platform, we are talking about an architecture with certain permissible parameterization. That means, when you are searching for that architecture, when you are searching for alternatives to do my task graph mapping, the set of possible architectures therefore gets defined on the basis of parameterization that is available on a platform, and that gives us a basic benefit in terms of design around platform. So, what is really a system platform? Because platform cannot exist independent of the software. One part of the platform is obviously the hardware platform. On top of that, we got to have software layer which wraps different parts of the hardware. You can have programmable cores, memory subsystem, all these things being managed via RTOS, I/O subsystem managed via device drivers, network connection via the network communication subsystem, and these three things together can form the API, and this API can be used for developing application on the platform, and this layer is called software platform. And combination of both hardware and software platforms is called the system platform. Okay. So, what will be the features of platform? In a sense, platform represents a partial design for a particular type of system. It includes embedded processors, may include embedded software through APIs, actually they do include software, and which can be customized to customer's requirement by changing the software or through component changes. So, once we have that, obviously this would enable design reuse. Design reuse can be achieved by sharing components among different products. This is called reuse in space. This can be also done across different product generations, which is called reuse in time. In fact, the whole idea of space is that if you are simultaneously developing two different products, in some way differentiated in terms of functionality, you can have your components shared between the products. So, that is why it is a reuse in space. Else, if it is over different generation of products, it would become reuse over time. So, effectively what are these products, or what are these, not really the products, what are these components? These components in a way are nothing but a library of functions and hardware and software implementations of these functions, which can be used across different designs. Okay. So, effectively if I have got a platform which talks about a parameterized hardware along with a set of APIs defined on top of that, and if we know different kind of functions have been implemented on this platform, and if we have them in a library, then for a new design, I can simply pick up those functions and use them in the design. Okay? And what is the advantage of this? Since they are being reused, the estimation of the performance parameters, which is actually the key point in doing hardware software co-design, becomes much more reliably calculated, generated or obtained. So, both at hardware and software level, we can do design reuse. By fixing hardware architecture, customization effort is entirely a software level, and basic software like RTOS and device drivers can be shared if developed using proper methodology. And what is interesting to note is that decomposition of system function is essential for design reuse. In fact, there is definitely a trade-off between the granularity at which you consider the system functions. If you consider them at a smaller granularity, then these functions may be common across multiple applications. Okay? So, then you can use those functions straight away. But if you are looking at a smaller granularity, then that may lead to increased complexity in the overall design. So, there is a basic trade-off between the two. But the key issue is that each application is unique in its own way. So, until and unless you can define a proper decomposition of a system function, you cannot really reuse the library components. That is why decomposition is an essential aspect of this kind of platform based design. So, what are the advantages? Any given space has a limited number of good solutions to the basic problems. So, what is this space? We are talking about an architecture space, that means different possible architectures, and that may be related also to applications. So, any given space has limited number of good solutions to its basic problems. So, when you are actually searching, if you look at hardware software co-design problem, it is basically a search problem. Now, where are you searching? You cannot search in an unbounded space. You would like to search among a set of possible good solutions. A platform captures the good solutions to important design challenges in that space. Okay? And that is why your search gets more focused, and through that you can actually reuse the good aspects of the good design. So, this leads to fast time to market, and you are reusing system design and hardware, both software, and allows chip to be customized to add value. Okay, that means using your software programmability or even hardware programmability on the basic design, you can add value. In fact, standards have actually encouraged development of these platforms as well, because when you are looking at embedded systems, the standards play a big role, because many of our appliances are catering to say wireless communication, multimedia appliances like your say MP3 player or DVD player, as well as network based applications, and these three domains are completely standards driven. Okay. So, standards defines the basic IO requirements, standards define the basic processing aspects. Okay. So, you cannot really have a DVD player which does not implement a DCT decoder, that is IDCT implementation, okay, because DCT forms a basic part of your MPEG coding scheme. So, in that sense, standards provide you a basic framework of functionalities which are to be implemented in the target appliance. Okay. So, standards that way actually motivates and supports platform based developments. So, developer chooses implementation of standards functions, improve quality, lower power, all these are issues, and products may be differentiated by added features. All of these cell phones, they provide the basic if they are working on the GSM standard, provide the basic GSM speech decoder. But the user interface can be different. All of them can store pictures in JPEG, all of them has to store, if they are storing video, in MPEG format. So, there the basic functionalities can remain same, but the user interface can be different, and this user interface can be implemented on top of your basic platform architecture. So, standards in that sense encourage platform based design, and today's whole approach for designing this kind of appliances are platform based. So, the trade off in this case is platform has many fewer degrees of freedom, that is absolutely true, and it is harder to differentiate, but can analyze design characteristics, that is something which is very important. On the other hand, if you want to build a completely full custom design, it would imply long design cycles. In fact, this is the basic trade off which really encourages this kind of development. So, for embedded system hardware platform, what do you expect in such a platform? You would expect processing unit, memory and I/O, but strong cost and packaging requirements make platform concept difficult to implement, because they can come with different kinds of requirements in terms of the cost and packaging, because packaging also decide the size. Variations in requirements of I/O systems makes architecture application specific. So, you cannot have all sorts of I/Os implemented in a platform, because many of these appliances actually differ in terms of their I/Os that they support. In fact, standards in a way help you to handle this problem, because standards tell you what kind of I/Os to be handled, okay, what kind of processing to be handled. But if you are looking at in a general purpose fashion, then these are two strong problems and difficult problems which are needed to be tackled for designing platforms. In fact, platform is a family of architectures that satisfy a set of architectural constraints that it as used to allow reuse. So, actually you won't encounter, or you won't like to have maybe a very general purpose platform. You cannot have that, because these are the two factors which makes that the platforms not possible for us to design platforms which are absolutely general purpose. So, in many cases they will be application specific. Now, application specifics will determine a set of constraints which that architecture should satisfy. So, let us take an example. This is a more of a conceptual example. Given a hardware platform, we define a hardware platform instance as a particular architecture in the hardware platform where all components are fully specified. So, in a platform architecture, some of the components may not be specified. Say for example, this is a conceptual model where it says that we may have a platform on which we can have CPUs, okay, of different speeds, we can have different I/O characteristics, and it can have different support for memory. And we can select an instance among this platform for implementation of my application. An instance will be what? An instance will be a CPU which operates at a particular speed. Depending my application, it can be a 30 MIPS CPU with a certain memory and capability of supporting maybe 4 digital I/O channels. So, that becomes application specific. And in this case, what is a platform? In this case, platform is not really a chip. If you look into it, platform provides you with a kind of a soft core kind of a framework, okay, and using this soft core framework, you can actually get the platform instance, okay, to implement your function. So, if you are searching for an architectural mapping, where we will be searching? You will be searching among the different possibilities that you can have with these combinations. So, you have been provided with say a soft core which can be effectively parameterized in terms of these parameters, and you are searching for the best core which would meet your requirement, and that is what is your application based platform instance. It is not a platform, but platform instance. On the other hand, if you look into it, so a fixed architecture with a programmable processor is a platform in this sense, okay, because a processor is indeed a collection of possible behavior, and a software implementation on a fixed architecture is a platform instance. So, in that sense, if you consider your PC using this definition, PC itself is a platform, because you can develop various applications on top of PC using pure software. Okay. A software implementation on a fixed architecture becomes a platform instance. Okay. So, what I had shown in these two examples is that in one case you can actually parameterize in terms of hardware characteristics, go through the synthesis process and build a platform instance which is meeting your application. Other extreme could be you can work with a fixed architecture and modify your software, okay, and software will define a particular platform instance meeting your functionality. Okay. Obviously, there would be variations of these which are in between. In fact, architecture platforms typically are micro architecture based. In fact, what we say is that platforms derive from a specific family of processors possibly oriented towards a particular class of problems. So, the platforms which provide the basic hardware architecture are typically built around some processor family. It can be an ARM family, it can be even around say other processors like your PIC family. So, they are typically built around a processor family, and many of these platforms are characterized by presence of programmable components. So, that platform instances can be derived from the platform. Now, this programmable component can come in variety of forms. One possibility is having a reconfigurable logic blocks like FPGA. Other possibility is software programmability. Okay. So, obviously, if I can put in the software, the behavior changes and you get an instance. On the other hand, I can program FPGA to implement some special functions depending on my application need to suit the platform. In fact, many of the platforms rely on embedded processors and not just a single processor, but a number of processors, so that their behavior can be customized through software, and that can put considerable design effort into the CPU, but that design effort goes in while making of the platform. And many platforms are therefore complex heterogeneous multiprocessors. Example is TI's OMAP, which we had already discussed, which has got ARM 9 as well as a DSP processors sitting inside. So, the behavior of these will be determined by mapping software onto those two processors, and that would give me a particular instance suiting my application. In fact, platforms use various kinds of intellectual property and soft cores like CPUs, memories, IO devices. And in a sense, platforms are IP at the next level of abstraction. So, if we are designing a chip using say pure soft core, so we are using IP at a lower level, okay, to which I can add my own memory. But when we are talking about that use of CPU, memory and IO devices, everything together, we are using IP at a next level of abstraction. In fact, one example we had already talked about, that we can think in terms of a pure soft core based platform where you may parameterize the architecture in terms of its processing speed, memory usage, IO channels, and then decide to fabricate that platform instance for your application. Okay. So, conceptually what we are talking about is, say this is my application space, okay, possible application, and I am dealing with an application instance. Okay. When I am dealing with an application instance, I know the basic properties and characteristics of the application, and then I need to do what we call a platform mapping, that is mapping in terms of system platform, that is your software as well as hardware. And you have got, if you look into this architectural space, so this architectural space consists of set of possible architectures. So once we have mapped this application instance to a set of software or hardware, in terms of here what we have got a set of functionalities depending on the application instance. So on the basis of functionality, we shall try to match them with different platform instances, because the platform as such would cover this architecture space, because platform has got a kind of a programmable component, parameterizable components. So a platform corresponds to a set of possible architectures. So instances of the platform covers this architectural space. Okay. And I have got therefore this platform instances. So this characteristics which is being mapped onto a system platform, that would lead to a platform instance. So let us try to understand what we are talking about. We are coming from application, got an application instance. Depending on an application instance, we have got a set of functionalities. These functionalities actually motivate us to make a choice about a system platform. The system platform corresponds to a set of possible architectures. I search among the set of possible architectures to choose a platform instance which will implement my application instance. So in a sense, if you see that your design process is not strictly a top-down design process. In fact, it's a one way is platform mapping, that is I am mapping to the platform, and next thing is the platform design space export, that is there are different possibilities in the platform design space, and from there we are mapping and trying to get the meeting point here. Okay. So this is the basic philosophy of what we call platform based design. So the design methodology is combination of top down and bottom up. The top down design define a set of abstraction layers. From specifications at a given level, select solutions in terms of components which are platforms of the following layer and propagate constraints. That means you got to know what are the components you require in terms of the functionalities that your application require, and those components would put in constraints, and that constraints you need to propagate to get to the actual instance. Okay. So when we are looking at a bottom up part of it, the platform components which are microcontroller, RTOS, communication primitives at a given level are abstracted to a higher level by their functionality and a set of parameters that help guiding the solution selection process. Okay. Because these two things have to match. Here we are coming from a top level abstraction in terms of functionality, and from bottom we are going up in terms of raw components, the microcontrollers, the basic RTOS, the communication primitives, and the bottom up process goes through a level of abstractions, so that these two has to match. If they do not match, then we cannot really do an implementation. So a design methodology becomes a combination of a top down and a bottom up process. In fact, hardware software implementation depend on choice of component at the architecture platform level, and function or architecture co-design happens at all levels of abstraction, because each platform is an architecture since it is a library of usable components and interconnects. And usable components can be considered as containers, and they support a set of behaviors. And mapping chooses one such behavior. Okay? And platform instance is a mapped behavior onto a platform. So, if we are coming from top, we are coming from application. Going up from the bottom, we are going from platform. And we need to do the mapping so that the functionality defines into behavior of a platform, and that behavior of a platform makes it a platform instance. So, take a very simple example from a software domain. Okay? Now, I can have an object representing a triangle, okay, and my problem is that of making a drawing, and that defines triangle with a certain set of parameters. So, these parameters have to be mapped to the triangle object, and I have to create an instance of the triangle object which realizes the drawing primitive. Okay? It is exactly like that. From function, what we are getting? From application, we are getting functional specifications, and from platform, we are getting components. We need to map functions to components. The mapping of function to components defines behaviors, and that would lead to a particular instance of the platform, which is actually your embedded system that you are designing. In fact, there are two phases of platform based design. So, what first phase is? Platform and the product. So, first thing is design the platform and use the platform. So, requirements and the past designs can motivate development of platform, and depending on exact product that you are developing, you will be developing an instance from the platform. So, if I go back to TI's OMAP example, depending on the requirements of multimedia communication, the features which are required has been analyzed, designs have been looked into, and different components have been put together to create the hardware platform as well as with the software support for it. And individual appliances, say a cell phone from Nokia, they would use the TI OMAP, say for example, with a particular set of functionalities, that is a particular set of behavior being implemented on top of that platform. So, in a sense, there is a division of labor, the platform design and platform based product design. So, platform design is choose, characterize hardware units, create the system architecture, optimize for performance, power, and platform based product design is modify hardware architecture and optimize your program so that you get the best performance. And in the context, the functional roles also diversify. Semiconductor house designs a platform, and systems house customize a platform for its system. Customization may be done in house or maybe through an external partner. So, here the example says TI is designing the platform and Nokia is developing the product. So, what are the platform design challenges? Does it satisfy the application's basic requirements? Is it sufficiently customizable and in right ways? Is it cost effective? These are the basic issues which are to be addressed. How long does it take to turn a platform into a product? Because if it takes lots of time to turn a platform into a product, then your platform will not be used. Okay? So, usability of the platform is also an important point. So, you cannot make your platform unnecessarily complex so that a user or an application developer cannot understand and use it. So, what is the methodology? Size the problem. What does that mean? That means you define an application, look at the space of possible applications, okay, and then have an assessment of size of the problem space. Size the problem essentially refers to sizing of the problem space, because an application can involve a number of problems, okay, and that problem space have to be assist. Develop an initial architecture, evaluate for performance and power, then evaluate customizability, improve platform after each use and get a better design. So, what we are telling in a way that platform must satisfy constraints of the application domain. Okay. Say if you look at the cell phone application, it should support the wireless communication, it should support the signal processing capability because I have to process a speech signal, I have to process a video signal, okay, and it should support also the various kinds of constraints, timing constraints of the application domain. And design of the platform is trade-off between size of the application space that can be supported by the architectures belonging to the platform and size of the architecture space that satisfies constraints embedded in architecture platform definition. Okay. So, these are the 2 points which should be very clearly understood. This talks about coverage of the application space. What are the different aspects of the application space are being addressed by the platform. These refers to the architecture space, what kind of flexibility you are giving to a product designer to explore alternate architectures for implementing functionalities. So, there has to be a trade-off between the two, because if you are trying to address the entire application space, then you may not be left with the flexibilities that can be provided to the final product developer, because your system may be complex enough to permit further flexible features. So, design is basically trade-off between these 2 aspects. Therefore, use challenges are what? How do I understand platforms design? How do I modify it to suit my needs? And how do I optimize for performance, power, etc. So, platform use methodology, start with reference design, because typically people do come with reference design. Evaluate differences required for your features, evaluate hardware changes, implement hardware and software changes in parallel, integrate and test. Okay. Wherever the hardware changes are possible, do the changes and integrate your software and hardware and do the testing. So, effectively what we are talking about is a design exploration, because once an architecture platform has been selected, then the design process basically consists of exploring remaining design space with the constraints set by the platform. Constraints can be on components as well as in communication. Okay. So, if you are looking at an ARM based platform and if that uses AMBA bus, then AMBA bus can be a constraint, and you may look at the possibility of designing with an additional FPGA with the ARM based platform. Okay, so, you are exploring the design space in terms of designs that can be mapped onto that FPGA block. And map, next part comes in is map functionality of application onto platform instance. Mapping process includes hardware software partitioning, which we already seen. But what is important, again I am repeating the same point, is that your possibilities gets defined by the constraints or the flexibilities that platform provide. Next comes use of software platform. The architecture platform is abstracted at a level so that application software sees a high level interface to the hardware. So, what would be the basic conceptual framework? In fact, in a sense, programming language is an abstraction of instruction set architecture. So, if even if the instruction set architecture changes, your application remains usable if you are developing the application using any high level language. An API abstraction of multiplicity of computational resources, that is your concurrency model of RTOS and available peripherals, that device drivers, that is abstracted through an application programmer's interface or the layer. Okay. So, that becomes the basic library of functions which would be used by your application program. So, in that sense your application software should be reusable for every platform instance. This is very interesting to note, because you might be changing your platform instances, but still if you are following these basic framework, then your application remains reusable. So, you can optimize your application by considering different instances of the platform without changing the software itself. So, the layered software structure looks something like this. So, at the top level you have got an application software which is sitting on top of your platform API. So, we talk about a platform API. In fact, TI's OMAP provide a kind of a Linux based APIs are available, and you have got this software, and this software layer of the platform would consist of device drivers, that is abstraction over the IOs, will consist of our RTOS, that is abstraction over the concurrency model, the model to support threads, processes, etc. And if you are actually looking at a distributed system, it should also have the network communication support. Okay. So, below that you have got your architecture platform, that is your hardware platform. Okay. And this hardware platform would be interfacing with the input and output devices. So, the whole application is being developed on top of this platform, and you have the ability to modify the behavior by changing the software part of it in terms of your application. You can even have the ability to change the architecture platform, some aspects of hardware architecture platforms through programmable or reconfigurable components. Even you can change the behavior by mapping, when it is a multiprocessor heterogeneous platform, mapping different parts of your application to different processes. Okay. So, this gives a layered software architecture for a platform based design. And then you do a verification, execute high level models, do co-simulation, run software on a sample chip, and finally check whether it is working or not. Co-simulation means simulation of both hardware and software. In fact, all these platforms do provide you with a development environment where you can do a co-simulation to check your design. So, what we have done today, considered platform based model for designing embedded system, explored features of platform and mapping problem. Multiprocessors rule high performance applications, and co-processors can be important for low power applications. In fact, we shall see more of these in next lecture. But what is interesting to see is that many of these platforms do support multiple processors in order to enable these kind of behavior. So, a basic problem becomes that also that of allocation. If you remember, we started today's class by considering the allocation problem. So, for such a platform based design, allocation and scheduling also becomes an important